Welcome to the Explainer. I am absolutely thrilled to guide you through this, because today we're tracing a truly fascinating evolution in computing history. We're going to explore how a deeply frustrating, almost comical computing struggle from way back in the 1950s quietly built the foundation for the incredibly fast modern navigation software sitting right there in your pocket.
To really understand the scale of what we're talking about, we have to look at a genuinely mind-boggling number, 10 to the power of 220. Now, if you want to drive from New York to San Francisco, you have to navigate the North American road system, right? And that contains over 64 million individual intersections. A simplified mathematical estimate means there are roughly 10 to the 220 possible routes you could potentially take. To put that into perspective, even if you could check a billion routes every single second, brute forcing this math problem would still take longer than the universe has literally existed.
Okay, let's dive into this. How exactly does a little rectangle of glass and metal in the palm of your hand solve an outright mathematical impossibility in just 4 seconds? Well, to figure out how we conquered this massive modern problem, we actually need to take a journey back in time to see exactly how the foundational pieces were put together.
Here's the roadmap for our explainer today. We'll kick things off with the 64 million intersection problem, dive right into Edgar Dijkstra's 1956 computing struggle, and look at his incredible 20-minute algorithm invention. After that, we'll see what happens when Dijkstra isn't quite enough, walk through a quick tutorial on pathfinding with hierarchies, and wrap it all up with a 70-year computing legacy. Starting off with Section 1, the 64 million intersection problem. The sheer scale of modern mapping networks is just staggering. Whether you're mapping out that cross-country drive or, programming a video game character to navigate a complex maze, the math is the same. And because checking every route takes longer than the lifespan of the universe, brute force is completely 100% off the table. We simply cannot check every option to find the absolute shortest path. So to solve tomorrow's problems, we have to look to the past.
Which brings us to Section 2. Dijkstra's 1956 computing struggle.
Let's travel back to 1956 Amsterdam. Meet Edgar Dijkstra, a brilliant mind working on software for an early computer called the Armac. At the time, the general public considered computers to be, practically useless. In fact, the perception was so bad that when Dijkstra applied for a marriage license, the municipal authorities literally told him programmer wasn't a real profession. There was no such job. As he later pointed out, his official marriage act hilariously and ridiculously lists him as a theoretical physicist. That is just how little the world understood computing back then. Moving right along to Section 3, the 20-minute algorithm invention. So Dijkstra desperately needed a specific, incredibly simple demo to prove to non-mathematicians that computers were actually powerful. While sitting in a coffee shop with his fiancée, he just asked himself a basic question. What is the shortest way to travel from Rotterdam to Groningen? And that simple question birthed Dijkstra's algorithm. He designed the whole thing in 20 minutes, completely without pencil or paper. Instead of just searching blindly step by step, his idea kept track of the shortest distance, or the cost, from the starting source to each surrounding node. By always asking, is the current path to this node the shortest we've seen so far, it prioritizes exploring low-cost paths first. Because it always explores from lowest to highest cost, it mathematically guarantees you will find the absolute shortest path to your target.
Let's move to the timeline and see how this builds. The algorithm flawlessly passed the Armac computer demo in 1956. But because algorithms weren't exactly seen as respectable for math journals quite yet, it just sat in his papers until 1959 when it was finally published in a brand new German journal. Fast forward a few decades to the 1990s, and the core engine of this exact algorithm was powering early manual GPS hierarchies. And today, it's still the beating heart of modern customizable contraction hierarchies.
Now for Section 4, when Dijkstra isn't enough.
Let's escalate the problem back up to our modern scale. If you run pure Dijkstra on the North American network, checking almost 64 million nodes, it takes about 7 seconds per path. When millions of people are asking servers for directions at the exact same time, a 7-second bottleneck is completely disastrous. We need it to run in less than a millisecond. And this brilliantly illustrates our core dilemma. Think of Dijkstra's algorithm like a circle expanding outward in all directions. It guarantees the shortest path, but it's just too slow at scale. On the flip side, we have A*, a modified version that penalizes going in the wrong direction, so it immediately heads toward the target. But here's the catch. Neither the brute force guarantee of Dijkstra nor the directional heuristic of A* fully solves the modern Google Maps problem by themselves. So you might be wondering, why not just use A*? Well, for one, A* relies on an extreme underestimate, straight-line distance. It also requires some really nasty square root computations that heavily slow down servers under load. If you only want the absolute shortest geographic distance, A* is great. Actually, fun fact, it's exactly why mobs in the video game Minecraft use it to chase you down. But if you care about optimizing true travel time for a real-life driving commute, a well-tuned Dijkstra actually beats it.
Section 5. Tutorial. Pathfinding with hierarchies.
When you're out driving, you rely heavily on human intuition. You instinctively know to take winding local roads for just a minute, hop onto a fast, major highway for the bulk of the trip, and then exit onto local roads again right at the end. Algorithms don't naturally know this. So let's look at the ultimate computing dilemma to see how we actually code that intuition into a machine. If we pre-calculated a massive lookup table of every possible route, the query would be instant, sure, but it would take over a decade to compute and require 8 petabytes of storage. Pure Dijkstra requires 0 pre-processing but takes 7 long seconds per query. But check out that bottom row, contraction hierarchies. With just an hour and a half of automatic pre-processing, the query drops to an incredibly fast 200 microseconds. It strikes the absolute perfect middle ground between memory and raw speed.
So the crucial point is this 4-step recipe for how a machine builds these hierarchies. Step 1, you find natural graph cuts. Step 2, you rank the nodes by importance. Step 3, you add math shortcuts for lower-ranked triangles so you don't accidentally miss local routes. And Step 4, you run a bidirectional search where the start and end points actually search towards each other, but only moving up the hierarchy of importance.
Let's physicalize this abstract math for a second. How does a computer know what a graph cut is? It literally looks for massive physical bottlenecks. If you want to drive across the United States, you almost certainly have to cross a bridge over the Mississippi River or drive through a pass in the Rocky Mountains. By identifying these massive geographical choke points, the algorithm groups the map into physical cuts and automatically assigns those bridge nodes the highest ranking of importance. It then nests smaller and smaller cuts inside of those, building a highly optimized hierarchy without a single human having to manually survey the roads.
And the final result is honestly breathtaking, 200 microseconds. By building this nested hierarchy and utilizing those mathematical shortcuts, the overall search space drops massively. Instead of checking 64 million nodes, the algorithm maybe checks just over 1,000. The query runtime miraculously plummets to 200 microseconds. To put that in perspective, that is a staggering 35,000 times faster than pure Dijkstra alone.
Finally, Section 6, a 70-year computing legacy.
Today, we rely on entire petabytes of data, massive sprawling server farms, and super complex DevOps just to keep everything running smoothly. But underneath all that modern mapping software, the core engine checking those nodes is still Dijkstra's coffee shop algorithm. A 1956 invention is literally still powering your phone. I think this quote perfectly captures his philosophy. Simplicity is prerequisite for reliability. Remember, he designed his entire algorithm without a pencil and paper. He later said that doing it entirely in his head forced him to avoid all avoidable complexities. That absolute, rigid dedication to simplicity is exactly why his algorithm easily outlived the early clunky mainframes it was originally written for.
You know, Dijkstra actually had a very touching hope for his legacy. He once said that if years later a programmer was about to do something quick and dirty, they would suddenly visualize him looking right over their shoulder saying, "Dijkstra would not have liked this." He wanted to enforce elegance from beyond. And I love that. That is the deeply human element hiding right behind the massive, complex, technological marvel we carry around in our pockets every day.
So, as we wrap up this explainer, I really want to leave you with a final thought. Even if you only control a tiny, small piece of a project today, your work can echo for decades. When you build something in your own corner of the world, what elegant legacy will you leave for the people who come after? Definitely something to think about next time you pull up a map. Thank you so much for joining me to explore this incredible journey today. Keep learning and stay curious.